This lesson is about process capability analysis. So what you're going to see is how you can compare based on some measurements that you get from the process, how you can compare how the process is doing with what the customer is expecting. So that's going to be based on some expectations of customers that you get based on market research, based on talking to customers, right? So we're making a comparison between customer expectations and the capability of the process. How is the process performing given the current conditions, right? So let's see how we can do that. So process capability analysis, this type of analysis can be used, first of all, only for measurement data. So we're using this for continuous kind of data where you're talking about time to serve the customer, weight of a particular item, those kinds of data. We're assuming a normal distribution of data as we do with a lot of things in quality management. To keep things simple, we assume a normal distribution. So we're assuming a normal distribution for this kind of analysis. And the most important thing here to keep in mind is that we will be doing process capability analysis with the assumption that the process is under statistical control. So what this means is when you're doing this in practice, you want to make sure that statistical control has been established, that you know the inherent capability of the process based on doing some kind of statistical process control analysis. So that becomes the first step before you go into doing a process capability analysis. From an intuitive perspective, that should make sense. It should make sense because what you're doing is you're going and talking to a customer and promising something. You're saying, are we going to be able to give you what you're expecting? In order to do that, you better be sure about how your process is performing. So from an intuitive perspective, it should make sense that you establish the capability of your process before you check for process capability based on customer expectations. Right, so let's take a look at some of the calculations that we'll do here. Basically, we'll look at two different ratios, the first of which is called the process capability ratio, or CP in short. Right? So what is the CP ratio? It's the ratio of what is the customer tolerance of whatever measurement you're talking about. How do we get the tolerance? You get it by taking the upper specification limit that the customer is giving you, subtracting the lower specification limit. Right? So you're getting the range of the tolerance for that particular measurement that the customer is giving you. So for example, the customer may be telling you, I expect this to be delivered between 20 and 25 days. So that gives you a range of 5 based on 25 minus 20. Or the customer might tell you, I expect the weight of this to be between 15.5 to 16.5 ounces. So that gives you a 1 ounce range for your tolerance. And that goes into the numerator of this particular ratio. Right. What you have in the denominator of this ratio is 6 times the standard deviation. So S stands for standard deviation, and that's what you get from your process. Right. So the numerator is coming from the customer, and the denominator is coming from what you measure in your process, what you find out from your process, how your process is currently doing. How do you interpret what you get from this ratio? You are looking for essentially a ratio that's greater than 1. Less than 1 is going to indicate that it's not capable of delivering to customer specifications. Greater than 1, 1 is going to say that it's just capable, and greater than 1 is going to say that it's better than being capable. Right? So the higher this ratio, the better it is in terms of serving customer expectations, in terms of keeping customers happy. All right, so where does this idea of 6 standard deviations in the denominator come from? So why do we have upper minus lower specification limit divided by 6 standard deviations? So the idea comes from the standard normal distribution. We rely on the fact that 99.7% of the observations are going to be between plus and minus 3 standard deviations, or the other words, plus and minus 3 standard deviations, right? So you have plus and minus 3, so you have a total of 6 standard deviations of range that you're getting, so that's what's going into the denominator of this particular ratio. Now, let's take a look at the intuition behind this particular ratio and see what we're getting here. So let's take a look at the voice of the customer here first. And what you have is the customer is telling you their tolerance range, right? They're telling you their tolerance range. And we can call that the voice of the customer, right? It's whatever the customer is telling you. And what you're saying is that this range, if you look at the width of this particular line segment, what you're saying is that that should be greater than the voice of the process, right? So what you're getting in terms of the variation in your process is being depicted in the denominator as 6 standard deviations, and that's your process range, which is being depicted by 6 times standard deviation. So when we're saying that we want this ratio to be 1 or greater than 1, a ratio of 1 would mean that this voice of the process and this voice of the process and voice of the customer are equal. If these are equal, that's saying that it's a ratio of 1. Right? And if the voice of the process is smaller and the voice of the customer has a greater range, then you're saying that the ratio is going to be greater than 1. So that's the intuition behind looking for a ratio that is at least 1, and the higher it is than 1, the better it is going to be in terms of serving the customer. Right? So let's take a look at the next ratio that is part of this process capability analysis, and that's called the CPK, or the Process Capability Index. So the Process Capability Index incorporates some more information than what we saw in the Process Capability Ratio. So what you have here is you have, if you look at the ratio that's given to us, the calculation, it's the minimum of the x double bar. It's called double bar because it's the mean of means. So it's the x double bar minus the lower specification limit, x double bar coming to you from the process, lower specification limit coming to you from the customer. Divide that by 3 times the standard deviation. And as this next calculation, you have the upper specification minus x double bar. That should be an x double bar divided by 3 times the standard deviation. So you're doing these 2 calculations and you're taking the minimum of these 2. Right? We'll take the minimum of these 2 and we'll compare it with that same standard that we had earlier. Is we want it to be 1 or greater than 1. 1 at a minimum, greater than 1 is going to be better. Lower than 1 means it's not going to fit into what the customer is expecting. So here we have the voice of the customer, right? What we had earlier when we looked at the process capability ratio. And the voice of the customer is given to us based on market research. There's a tolerance range that's given to us. Now here, these specific numbers matter. Why do they matter? Because we're not just comparing this range with the other range, this range with the process range. We're comparing this with where that process is located. So if you noticed earlier, I just looked at whether that range of the voice of the customer was greater than the range of the voice of the process. But here, I'm not only looking at whether it's greater, but where it is situated in relation to each other. So if this is the voice of the process, right, this is based on there being some kind of mean over here, which we refer typically as x double bar, and this is going to be based on your plus or minus 3 standard deviations. Right? So in this particular example, you're seeing just on the basis of this picture that there will be output from this process that's going to go beyond the voice of the customer. So what is this telling us? That this process is located, is centered too much to the left. Now, if you look at the range that we had in this process, this range is smaller than the range of the tolerance of the customer. So in that sense, what you're going to get if this was, if we were to put numbers on this, you're going to get a process capability ratio that's going to be okay. That's going to be greater than 1. However, because the mean is too low, even though the range is compatible, it's falling within what the customer is expecting, it's located too far to the left, and therefore you're going to get output from this process that's going to fall outside of the customer's tolerance range. So that's the intuition that you have behind the process capability index. Now let's take a look at an example to see how this plays out. So here we have a restaurant on the Magnificent Mile in Chicago that promises quick lunch meals of high quality from a limited menu with some customization. Market research has determined that the customers that come in there, they're mainly people who are working in the offices on Michigan Avenue and in nearby offices, or they are tourists who are walking in there to get a quick meal. They expect their orders to take between 2 and 16 minutes. So what is our customer expectation? The lower specification limit, or the LSL for customer expectation, is 2 minutes. The upper specification limit is 16 minutes, right? They're expecting that because of the customization, it can't be 0, so it's going to take at least 2 minutes for it to get done, but they're expecting it to be done in a maximum of 16 minutes. That's their expectation. When you go and look at the actual process, when this restaurant assessed their actual process, they found the average turnaround time from order to arrival to be 12 minutes. So this is coming from the process. This is coming from data collected about the process, and they find an average of 12 minutes and a standard deviation of 2 minutes. So the question is this process going to be capable of conforming to customer expectations? Now, remember that we are assuming that this process is in statistical control, that the 2 and 12 represent the inherent capability of the process. So in that sense, we are quite confident of the 2 and 12 when we're comparing it with the 2 and 16, right? So the standard deviation of 2 and the mean of 12, we're quite confident about that when we are comparing it with the specification limits given to us by the customer. All right, so let's do some of the calculations and see what we can find. So what we're going to calculate is the CP and the CPK, process capability ratio and the process capability index. Both of these have to be calculated at all times. You can't do one without the other. All right, so let's take a look at the process capability ratio first. Upper specification limit of 16, lower specification limit of 2. We subtract 16 minus 2, and we divide that by 6 times the standard deviation. Where did the 6 come from? That's part of the formula that came from having plus or minus 3 standard deviations. So we use that property of the normal distribution, and the 2 is the standard deviation in the denominator. In the numerator, you have the upper and lower specification limits coming from the customer. Ratio works out to greater than 1. You can see that the numerator is greater than the denominator. So it fits into the range of the process, fits into the range of the customer in this case, right? Let's look at the next thing, and that's going to be your process capability index. Now, if you notice here, before we get to the process capability index, I said the process has the potential of being capable. Because remember what we saw in the picture earlier, that you can have a range that falls within the customer specifications. You can have a process range that falls within the customer range. However, it might be located in terms of centering of that process. It might be too much to the left or the right. All right, so let's take a look at the process capability index. The calculations are going to be based on, we need to do 2 calculations based on incorporating the mean of the process. So here we're actually going to use that average service time of 12 minutes in our calculations. If you noticed in the CP calculation, we had nothing to do with the 12 minutes. We simply relied on the 2 minutes of standard deviation. So we're going to take the minimum of these 2 ratios, and when you calculate these through, you get 1.67 and 0.67. So what is this telling us? It's telling us that there's going to be a problem. Right? We find a ratio that's less than 1. It's telling us that this process is not capable of serving this customer. In fact, it's telling us that the mean is too far to the right. Now, how do we know that? 2 ways. You can look at which of those 2 ratios gave us a 0.67, and you'll see that it was on the upper side. When you did 16 minus 12, that's where you got the number that was less than 1. So that's telling us that it is going to be on the upper side. You can also simply take a look at the upper and lower specification limits and compare with the center of the process that you have from the process average, right? So if you look at the center of the upper and lower specification limits of the customer, it's between 16 and 2, so that's going to be at 9, right? So you have 2 plus 7, 9, 7 plus 9, 16, so 9 is the center. And then you can see the average service time of 12 minutes is higher than 9. So it's too much to the right, too far to the right, and that's why you have times that are going to be higher than the upper specification limit coming out of this process, right? So this gives us a quick indication that this process is not going to be capable of serving these types of customers. They're going to be unhappy customers. So overall interpretation, the variability seems to be okay. It's low enough for us to fulfill customer expectations, for the restaurant to fulfill customer expectations, but the average is too high. What can this restaurant do? It can do two things. It can reduce the average, get it to 9. By getting it to 9, it's going to have a process that will look capable of serving the customer expectation, or you can reduce the standard deviation. So if the restaurant were to make their process more predictable, have the standard deviation of their process reduce, let's say from 2 to 1. Right now their standard deviation is 2. If they can have that standard deviation to 1, that would also make the process capable. Now, which one this restaurant is able to do, that's going to need more information, right? I mean, whether they can actually reduce the time that it takes, it may not be able to reduce the average time based on the kinds of orders that it gets and the kinds of things it needs to do to produce those orders. Can it reduce the standard deviation? Maybe based on different training of different people who are working in the kitchen and different training of different people who are serving and taking orders outside. There might be some things that can be done to reduce the variation, to reduce the standard deviation of the process. And if that can be reduced, then the process will become capable of serving these kinds of customers. You'll get a ratio that is going to be greater than 1, both in the case of CP and CPK, right? So in summary, what we're saying is that the process is capable when you have a process capability ratio as well as a process capability index, both being 1 or greater. 1 is a minimum, greater than 1 better, the higher the better, right? So let's take a look at this whole idea in terms of pictures. What are we saying here? So if a process is capable, this is how it will look, right? You have the center value of 9. We can call that the nominal value that the customer has given us. So we have a lower specification limit of 2 minutes, upper specification limit of 16 minutes. The 9 minutes is the nominal value. That's the center value. That's the ideal value that the customer is expecting. What we're saying with a process that is capable is we're saying that the process distribution falls within the lower and upper specification limits. Picture this with a process that is not capable of serving these kinds of customers. So we're saying that we found the process to be centered too far to the right. It was centered, the mean was 12 minutes. So if you look at 12 minutes and the standard deviation going from 12 minutes towards the higher side, it was falling too much to outside of the upper specification limits. So you needed to either shift the mean or reduce the standard deviation, get this distribution to be tighter to for that red graph that you have to fall within 2 and 16, more importantly at less than 16, right? So that's an interpretation that you can see in terms of pictures. All right, so let's take this and try to apply it in terms of different scenarios. So what you'll see in the next slide is you'll see 4 different situations based on customer specifications and process distribution being depicted. And what I would like you to do is for each situation, just think about what it's telling you in terms of whether this process is going to be capable, or whether the process capability ratio and the process capability index will be 1 or greater in each of these cases, simply based on looking at these pictures. No numbers here, simply looking at pictures and being able to say whether each of those, whether the ratio and the index are going to be 1 or greater in each of these cases. So take a look at these pictures now. So what can we see from here? We can see that when you look at the scenario A, the customer specification is much wider than the process distribution, right? So the process capability ratio is definitely going to be greater than 1. It's going to be quite larger than 1, simply because the denominator of that ratio is going to be much smaller than the numerator. The customer specification is what goes into the numerator. The process capability index is also going to be greater than 1, simply because the process is centered exactly at where the customer specification is, right? So that's scenario A for you. For scenario B, what can you say? You can say that each of those, the ratio and the index, both of them are going to be exactly 1, right? The variability in the process, if you look at plus or minus 3 standard deviations, makes up exactly the customer specification range. So if you look at upper minus lower specifications and you compare that to 6 times the standard deviation, this is telling you that it's going to be exactly equal. So the ratio will be 1 and the index will also be 1 in this case, because it's centered exactly at the nominal value of the customer. Let's take a look at C. What can you expect there? C is clearly going to be a case where your process capability ratio is going to be less than 1. Process distribution is much wider than customer specification. So right off the bat, you can say that you're going to have a lot of output from the process that's falling above and below customer specification. The CP, or the process capability ratio, is going to be less than 1. The process capability index is also going to be less than 1, simply because you have points that are outside of the upper and lower specification limit of the customer. So what you can actually infer from C is that if you have a process capability ratio, if you have a CP value, so a process capability ratio that is less than 1, there's no point of even calculating the index, the CPK, because then the CPK is also going to be less than 1. In other words, what you can generally say is that the CPK value is always going to be either equal to or less than the CP value. Right? So if you've already calculated a CP value that's less than 1, the CPK value is either going to be equal to that or less than that, so there's no point of even looking at the CPK value. In terms of scenario D, what do you see there? You see that the customer specification, the range that you get from that, and the process distribution are equal, so the process capability ratio will be exactly 1. However, the process is centered too much to the right. The average of the process is too much on the higher side, so you're going to get a lot of output, or you're going to get output that's going to be beyond customer specifications on the right side. So that's going to be a case of CP being 1 and CPK being less than 1. So let's take an example now of a situation where you don't really care about both sides of the ratio. So we looked at the time that it took at a restaurant in the previous example, and there may be situations where you say, look, I expect the time to be 0, right? It should be instantaneous. If I'm talking about a fast food restaurant, then it's curtailed at 0 on the left side. Your expectation of the customer is 0. Another example that you can think of is when you're looking at something like a roughness of cloth. Well, customer expectation is going to be that the roughness of cloth is not there, that it's perfect, that it's smooth, and therefore you don't have anything towards the lower specification limit. All you have is an upper specification limit that you can tolerate. So let's take a look at an example of that and see the difference in calculations there, and how you would go about looking at the process capability there. So here's a fast food restaurant now, and the customers expect orders to arrive in less than 3 minutes. So in other words, we're saying 0 to 3 minutes, right? So it's lower specification of 0. Current process is at a burger joint, Leslie's Burgers. delivers orders in an average of 1 minute, so X double bar is 1 minute, and a standard deviation, or S, of 0.5 minutes. Is the process capable of conforming to customer expectations? Right. So since we don't have a lower specification limit here, the calculations are going to be slightly different. So let's take a look at these calculations. So when you don't have a lower specification limit, or the lower specification limit is 0, you basically do not even need to look at the process capability ratio. It's going to be meaningless, right? Because there's no, it's bounded on the left side, so you don't really have a meaning of comparing the range of what the customer is expecting to the range of what your process is doing. In calculating the CPK, you're only going to care about one side. You're not going to look at the minimum of both of them like you did in the previous example, but you're only going to care on the upper side in this case, and that calculation in this case works out to 1.33, so it's telling us that the process is capable of fulfilling customer expectations. So when you're dealing with a one-sided specification limit, you would go about it in terms of simply calculating the CPK and a one-sided CPK. You're not even going to calculate both sides for that particular for the particular index. So in general, what are the uses of the process capability? So it gives a quick indicator of the chance that this process, or what you're getting from the process, is going to fulfill customer requirements. If you scrutinize the idea of process capability analysis, and if you're familiar with statistics in general, it's not giving you any new information other than simply comparing the mean of the process and looking at, when you go plus or minus 3 standard deviations from the mean of the process, whether that falls within the range of upper and lower specification limits. So you're not getting any new information more than that, but it's giving you a quick indicator. So thinking about it in terms of process capability ratio, an index of 1, a minimum of 1, tells you that it's going to fall within specification limits or not. It gives you the ability to compare this particular metric across different processes. If you have different suppliers who you're considering or you're comparing, you want the CP and CPK to be higher for the suppliers that you choose, so you can do that. It helps you think about the cost calculations for supplies that you're getting from particular suppliers. The higher the CP and the CPK numbers of suppliers, the lower the chances of you getting defective raw material, the lower the chances of you having to work with defective raw material and get defective product at your end. So that gives you a sense of calculating costs from different suppliers. It becomes an effective tool in terms of giving specifications to suppliers. You can use this ratio and index to tell suppliers what you expect in terms of the process capability ratio, or the process capability overall for particular items that you're dealing with.